Today we will discuss about the technical report. That's a derivation of logarithmic decrement from energy dissipation in lightly damped structures. It's kind of like we are finding out how the logarithmic decrement can be found from the energy dissipation in case of lightly damped means undamped systems. Objective to derive expression for logarithmic decrement. So logarithmic decrement, we just want to find the expression for it in terms of vibrational energy. Energy is u, we are measuring it, and the energy dissipated per cycle. So each cycle that's the energy something is going out of the system, that's because of the damping. So how much that energy is going out of the system, that's the energy dissipated per cycle, and how much energy, total energy, vibrational energy, and what's the logarithmic decrement. So we are going to find out from the logarithmic decrement from these two terms, u and delta u, for a lightly damped single data frame structure. This provides a physical meaningful relationship between the damping and energy loss per cycle of vibration. So what's the relation between the damping and energy loss? That we are going to find out. Physical background: in real world structures, all on the mechanical systems, damping causes energy to be lost over time. So energy is lost because of the damping. Over time energy is losing, right? That's because of damping only, usually through the mechanisms of friction and material hysteresis. This we will talk about it: material hysteresis and air resistance. So through three mechanisms of friction, material hysteresis and air resistance. For lightly damped systems, this loss of energy is gradual. The system continues oscillating with a slowly decaying amplitude. Only in case of lightly damped structures, only the oscillation happens, and it slows. The amplitude is decaying slowly. Each cycle of oscillation dissipates a small amount of energy. So from one cycle to another cycle, the small amount of energy is getting lost. This is observed as a reduction in the peak displacement of each cycle. That's how we observe it. Like first cycle the peak is higher, and second cycle peak is coming down. So slowly the peak is getting reduced. If you take, this is the time and this is the amplitude, the peak at each cycle is getting slowly damped out. And to quantify the damping in such systems, engineers we use a quantity called logarithmic decrement. That's a logarithmic decrement which measures the rate of exponential decay in amplitude between successive cycles. How the amplitude is decaying, exponentially it's decaying, that measured by this logarithmic decrement. So logarithmic decrement is defined as a natural logarithm of a ratio of amplitudes in two successive cycles. So this is the first cycle amplitude and this is the second cycle amplitude. The ratio between these two successive cycles, amplitude of these two successive cycles with the natural logarithm, that's how we found out the logarithmic decrement. X1 is the amplitude of start of the cycle, x2 is the amplitude at the end of the same cycle next week. For lightly damped systems, x2 means the next cycle, the amplitude, next cycle amplitude, that is not equal to first amplitude, but it is with reduction in the amplitude height. That reduction is exponential power minus delta. So x2, next amplitude of the next cycle is amplitude of first cycle multiplied by reduction factor. It's going to reduce, right? So if you see the cycle, it's a high at first and second is less and third is less, like that it's going, right? So amplitude of first cycle x1, amplitude of second cycle, so second cycle x2 is almost some value lesser than this x1 value, that's e power minus delta, and hence the damping causes the peak amplitude to decay exponentially with each cycle. So with each cycle it's going to exponentially it's decaying, this exponential curve, exponentially each cycle is decaying. So vibrational energy in the system. The spring mass system without damping, energy is exchanged between kinematic and potential forms. At the point of maximum displacement, all the energy is stored as potential energy. So if you have a pendulum, something like this is a pendulum. When it is moving up, this is a position, that's a maximum position. All right. So at this point it stored the energy, right? That's the potential energy stored. This is the height. So potential energy is half kx squared. K is the stiffness of spring, x is the maximum displacement. That's amplitude. So x1 amplitude at the beginning of the cycle, x2 is the amplitude after the one cycle, that is x1 e power minus delta. So u1 we can say half into k1 into k into x1 squared, ut equal to half into k into x2 squared. X2 we can write it x1 e power minus delta, right? So square becomes x1 square e power minus delta square, so e power minus 2 delta. So energy dissipated per cycle is energy lost is the difference between the u1 and u2, that's half into k into x1, because x1 is higher, so energy is higher here, and minus u2 we can write half into k into x1 squared into e power minus delta. That's why we can put it 1 minus e power 2 delta. The energy loss, this energy represents the damping loss due to the internal and external resistive forces. Approximation for small damping. For lightly damped systems, delta is very less than 1. So using the first order Taylor expansion of the exponential, e power minus 2 omega is 1 minus 2 omega. E power minus 2 delta, we can say delta is 1 minus delta, approximately 1 minus 2 delta. This is the value for e power minus 2 delta for delta less than 1. Then we have delta u as 1 minus k into x1 square 1 minus, instead of e power 2 minus e power minus 2 delta, we can write 1 minus 2 delta. So 1 minus 1 it get cancelled, and this minus get plus, so it's a 2 delta. So approximately half into k into x1 square 2 times delta is coming. Half into k into x1 square is nothing but the u1, right? u1, right? So delta u is approximately u1 into 2 delta. That means delta logarithmic decrement is, it goes here and u also goes below. So change in energy loss divided by 2 times original u1, right? So this is how we can find out the logarithmic decrement. So physical interpretation. The logarithmic decrement delta tells us how quickly the vibration dies out. If it is more, that means very quickly the vibration dies out. Small delta means low damping. System vibrates for many cycles before stopping. If the logarithmic decrement is small, system is going to vibrate for many cycles before stopping. And the ratio delta U is the fraction of energy lost per cycle due to damping. The formula is links physical energy lost to a measurable quantity, decay in amplitude. With the decay in amplitude, we can find out the logarithmic decrement. Delta is a compact way to express the damping via energy decay. How the energy is getting decayed, that's by finding out how the energy is decaying. From that we can come to know the delta without needing to model specific damping forces directly, right? Applications, it's used in the structural dynamics. This method used to estimate the damping from experimental free vibration test. Engineers measure successive amplitudes from a time history of vibration. Then we can find out delta is approximately natural logarithm of x1 divided by x2 to estimate damping. With this result, damping can be related to energy absorption capacity. So conclusion, we have derived that for lightly damped system, delta equal to half of delta u by u. It's a measurable amplitude decay. This relation provides a powerful and intuitive link between the measurable amplitude decay, that's a measurable amplitude decay, and underlying energy loss due to damping, quantifying the damping from the experimental data. So there's a discussion between lead engineer and trainee. Alright, let's talk about the damping and how we measure how fast the structure stops vibrating. Let's measure how fast the structure stops vibrating. Specifically, we will look at something called logarithmic decrement, or just delta. You can say this is a delta. Okay, it helps us understand how much energy is lost in each vibration cycle. So there's a multiple number of cycles is going to happen, and each cycle how much energy is getting lost, that we can measure it by using this delta. Okay. And also we can measure how fast or how many number of cycles it's going to take before it dies down, or before the vibration stops, how fast it's going to stop. That way we can measure it. So delta is just the rate at which amplitude decreases. Delta is just a rate at which amplitude decreases. Exactly, if you watch a building or machine part vibrate after shock, it gets the peak gets smaller and smaller. If you watch a building or machine part vibrate after a shock, if some after some shock happens, the building or some part of the machine is vibrating, right? That peak, if you see it, it's getting smaller and smaller. Delta tells us how quickly that happens. Delta tells us how quickly that happens. If delta is very high, that quickly the amplitude decreases, and delta is low, it takes more number of cycle, and amplitude decreases very slowly. It's calculated using this formula. That's the natural log of the ratio of two successive peak displacements. What does that have to do with energy? Each time the system moves, it stores energy in the spring, right? Like stretched rubber band. The energy at peak is half into kx squared. Half into kx squared. Because of damping, some of that energy is lost every cycle. Because of damping, only energy is lost at each cycle through heat, friction, and internal material behavior. Material hysteresis we used to talk about, right? That's internal material behavior. How much energy is lost each time? How much energy is lost each time? We call delta U the energy lost in one cycle. Mathematically, it's the difference between the energy in the first peak and second. Delta U equal to U1 minus U2. So for small damping, we can simplify and say delta. So that means delta is just half of the energy loss ratio. And gives the key formula. It tells us that more energy the system loses per cycle, larger the delta, and faster the vibration dies out. It means what? If the more energy is lost in each cycle, so energy quickly it will go out, right? That means the vibration dies down faster, and the delta logarithmic decrement is also higher value. We can use this to measure the damping from test data. So absolutely, you just measure two successive peak displacements during free vibration test and plug into the delta formula. From that, you can estimate how much energy is being lost. This is used all the time in structural testing vibrations. Delta is the logarithmic increment that tells how fast the vibrations reduce. So from delta, what can we understand? How fast the vibrations reduce. Each cycle some energy is lost, so each vibration cycle some energy is lost. That's we can understand from its peak is getting smaller and smaller also. From if the system loses small amount of energy, delta is small, that means slow decay. If the energy loss is very less, then small decay. For light damping, delta is almost half of energy lost per cycle into energy stored. Half of energy lost per cycle divided by energy stored. We use this to estimate the damping from vibration test. We can have further more discussion. Alright everyone, take a good look at this graph. Notice that how the peak gets smaller and smaller one after the other. That's damping, right? The system is losing energy. Exactly the curve you see is not just math. It's sound of a machine winding down the echo after a bridge shakes, after shocks of earthquake. Damping is nature's way of telling calm down. Damping, we can say in other way, it's a nature's way of telling calm down. Damping is the one thing that makes the vibrations to die down, right? That makes like things to get calm down, right? So that's the nature's way of saying calm down. So but how do we measure that calm down effects? It's not like we can see the friction. We cannot see the friction, right? It's not like we can see the friction or hear the energy loss. We measure it through something called logarithmic decrement. So how we can measure it, that calm down effect, means through logarithmic decrement. Think of it as a whisper that tells us how quickly the vibration fades. It tells that it's going to quickly, it will vibrate, fades away, or it's going to take much longer time to fade away. So mathematically, it's a natural logarithm of two successive peaks. That's no magic, just amplitude decay. So if the peak drops slowly, it means delta is small. If it drops quickly, delta is large. You understand, right? If the peak drops slowly, the delta logarithmic is small. If the peak drops quickly, delta is large. Spot on. And delta is the pulse rate of structure. It tells us if it's relaxing slowly or collapsing fast. So why use log and ratios when we can just measure the energy loss? Isn't that more direct? Let me show you why. Let's say spring or system is vibrating at its maximum stretch, all the energy is stored in the spring. So when the displacement is more, all the energy is stored in the spring because that's going to pull back, right? So this is the vibration energy. We can say half. So force and displacement, right? Force into displacement. Fx is the force, and the displacement is the how much the spring has moved. This is the force. K into x. K into x is the force. K into x is the force. X is the displacement. Half into fx into u. That means if you see the curve, this is the displacement, this is the force. Suppose if you take like that, 0 force, 0 displacement, 1 force, little displacement, 2 force, 2 times displacement, 3 force, and this is the 3 times displacement, 4 force, 4 times displacement. It's going to be like linear. So the area under this curve is the work done, right? That's why the area is nothing but a triangle area, right? Half into x is, this is the value displacement, how much displacement happens, and this is the force we can find from the stiffness into displacement. That's why half into this kx we can say a force. So half into force into displacement, or half into kx into x. That's why half kx squared. Okay, that's why vibration energy after one full cycle, if it still stretches but not as much, so the energy is bit less. After one cycle it still stretches but not as much, so the energy is bit lost because damping took some energy away. Who is taking some energy away? So basically damping is stealing some energy away, right? So yeah, some energy is getting lost because of damping. So energy loss is we called delta U equal to U1 minus U2. This is the energy loss, but we know x2 second cycle peak is lesser than the first cycle peak, and it's exponentially decaying and negative. Why we are putting minus? Because it's negative, it's coming down. This is the delta value, it's exponential. Okay, this is our peak for the next cycle. If someone is asking if someone is giving you the peak for first cycle and delta value logarithmic decrement, and they want us to find out the next cycle's peak value, you can use this formula. So simplifies energy loss is delta U is approximately 2 times delta U. Real world application. This is from a test we did on the footbridge after it started resonating when pedestrian crossed. People were scared if it felt like the bridge was bouncing back at them. I read about that happening in London once. Engineers panicked. Rightly so. Structure like bridges, floors, even stadium stands have dangerous oscillations. In this test, we induce a small vibration recorded the decay. So this is a waveform. So the amplitude dropping, can we use that to find the delta? Let's walk through it. First, take the two successive peak displacements, 12 and 10.8. So calculate delta. That's not a huge delta, but it's not a tiny either. If we plug that into energy loss, then we will find it. That means 21% of energy is lost per cycle. If you put that in the formula. Yeah, that's a lot. For something like a footbridge, you want minimal damping, but not so slow that vibrates uncontrollably. It's strange, these numbers, they are not just they are comfort and safety. Think about it, stadium full of people jumping in sync. If the damping is too low, the structure resonates like a tuning fork. If it's too high, it feels rigid, unnatural. We need balance. It's like a tuning the guitar string, enough tension to ring and enough damping to stop. Engineering is music written in maths. Engineering is like a music written in maths. So alright, challenge time. Let's say you have a machine part that vibrates at a small amplitude. You measure 4.95 and 4.9. Can someone walk through the full process? So delta, it becomes 0.0202. That means delta U by U equal 2 times delta, right? So 0.04. That means 4% energy is lost. Delta U by U is delta U by U equal to 2 times delta. So energy loss is 4% per cycle. Well done. That's how we link vibration data, damping ratio, energy behavior. And once you have this, you can make the critical decisions, the reinforced structure, adjust the material, add dampers. I never realized how much insight we can get from these just 2 points of data, 2 amplitudes. That's the beauty of engineering. From something as small as peak height, you can predict failure or safety or longevity. Delta becomes your guide. So the next time we walk across the bridge, feel a machine humming, we will remember this. Alright, let's expose something fundamental but powerful. How do we understand how much energy a vibrating system loses every cycle? And how can we measure that using just 2 points? Is that what logarithmic decrement is about? Measuring energy loss? Yes. In a very elegant way, we usually can't measure damping forces directly in the field, but we can record how much amplitude drops after each vibration cycle. From that, we can calculate the number called logarithmic decrement. Logarithmic decrement we can calculate from using natural logarithm of x1 divided by x2. Just finding out the vibration amplitudes, we can calculate the natural logarithmic decrement. From that, we can somehow get into the damping force. Delta is how fast the peaks drop. Delta source. Delta is just how fast the peak drops. Exactly, think of it like this. If the system vibrates and each peak is lower than the last, and delta tells how steep that drop is. So if the first peak is 10 and second peak is 9, we can already get delta. Spot on. The formula is, this is the one, so we can get the delta. This number is small, which means damping is light. The system takes several cycles to stop. Because of undamped structures, the system takes a bouncing effect and it's going to oscillate and then it will stop eventually. But if it is this delta value is very high, it's 1 or something like that, that's critical damping. System is not going to vibrate, it will stop. If it is more than 1.0, it's like over damped, it will not vibrate, but it will come to the original position slowly. That's kind of dragging. But what's happening physically during that time? If the system is giving off a heat, system is just giving off heat, yes, energy is dissipated. It can be lost. It can be lost as heat or friction or internal material damping. Every cycle, the system lost a bit of its energy stored. Every cycle, the system loses a bit of energy stored, and that stored energy, that's in the spring, right? Like potential energy, yes. So correct at the peak of each cycle, all the energy is in the spring. At the peak of each cycle, all the energy is in the spring, and it is U equal half into kx squared. The moment the amplitude drops from one cycle to next, we know energy has been lost. When the amplitude drops from one cycle to another cycle, we know the energy is been lost. How do we relate that energy loss to delta? How do we relate that energy loss to delta? We connect the dots. If u1 is half into k1x squared, u2 is half into k2x squared, then energy lost is u1 minus u2 is called half into x1 squared. If you take it out, 1 minus x2 by x squared whole square, right? So that's e power delta. So you can get approximately delta u equal to 2 times delta u1, so we can get delta equal to half into delta u by u. We have just shown how delta is half the fractional energy lost per cycle. So if a system loses 10% of its energy each cycle, delta is 0.05. Alright, if energy lost each cycle is 10%, then delta is half of that. 0.1 divided by 2 is 0.05. So 10% energy is lost, then delta becomes 0.05. That's a practical way to read it. Delta gives us a scaled measure of how much energy is bleeding out of the system. So delta gives us a scaled measure of how much of energy is bleeding out of the system, and we only need to measure 2 peaks. That's sufficient. That's why engineers love it. You can run a simple test, grab a structure, record the free vibration, grab the 2 amplitudes, and you know how well it dissipates energy. Alright team, today we are going to talk about an important concept in vibration. It's called logarithmic decrement. That's simplified by delta. Okay, it helps us understand how fast the vibration amplitude decreases in a damped system. If you see in a damped system, the vibration amplitudes are going like this, right? So we are trying to understand how fast the vibration amplitudes decrease in a damped system. So does delta tell us how much damping the system has? Yes. More specifically, delta measures how the amplitude drops from one peak to another peak in a vibrating system, even if we can't measure the damping force directly. So delta tells us, let us infer damping from these vibration amplitudes. Just from these vibration amplitudes, we can infer damping. So look at this free vibration response. The peaks slowly get smaller because of damping. Let's say the amplitude of one peak is x1 here, and this is the next peak is x2. The logarithmic decrement is defined as natural logarithm of x1 by x2. So it's just a natural logarithm of the ratio of two successive peak amplitudes, right? So exactly this ratio shows how much the vibration amplitude decreases every cycle. Since the amplitude decays exponentially in a damped system, taking natural logarithm converts this exponential decay into a linear relationship, which simplifies the analysis. Why exactly does the amplitude decay exponentially? Why exactly the amplitudes decay exponentially? This is exponential. Why does it decay exponentially? Why exactly does the amplitude decay exponentially? The displacement in a damped harmonic oscillator varies like this. This exponential is the exponential term. This e power minus rho into omega and d. That's the exponential term that causes the amplitude to reduce over time. Damping continuously dissipates energy. Because of the damping, energy is getting lost every time. So damping continuously dissipates energy. So vibration amplitude shrinks exponentially. So this amplitude x1 and x2, it just shrinks because of the damping. It shrinks exponentially because of the damping. Can delta be related to the energy lost in each cycle? So can we relate this delta to energy loss, delta U, in each cycle? Yes, absolutely. The vibration energy is stored at the maximum displacement. The spring's potential energy when this spring is pushed, then are stretched. So it's stretched. So this is why energy is stored in the spring, right? So maximum energy is stored in the spring, that is a half into k into x squared, spring stiffness into displacement. Okay, so at first peak, the energy with the displacement x1 energy is half xn squared. Or the next peak, x2 is x1 e power minus delta, because of this first peak and second peak. If you see, the first peak x1 and second peak is x2, that peak is x3. So these are exponentially decaying. So that's why x2 is, we can write x1 into e power minus delta. So we can write u2 as half into k into x2 squared, that is half into k into x1 squared and e power minus 2 delta. So delta U is the energy lost, u1 minus u2, we can see half into k1 x squared, we can take this as a u1. So u1 into 1 minus e power minus 2 delta. This 1 minus e power minus 2 delta, we can simplify this into 1 minus 2 delta. So the delta u, we can write it half into k into x into 2 delta. So it becomes 2 into delta into u1. So it is just, we can say the logarithmic decrement is this is half the ratio of energy lost in each cycle to the energy stored in the system. This is the energy stored in the system. Delta is the energy lost per cycle. That's the energy lost each cycle. Energy lost each cycle is the delta U. Half the ratio. This is half. This is half the ratio of, what is the ratio of delta U by U? Whatever the ratio comes, you multiply that by half, so you will get that logarithmic decrement. So exactly, this gives us delta a very clear physical meaning. It quantifies how much energy dissipates per cycle related to the total vibration energy. So we know what is the total vibration energy, how much energy is dissipated per cycle. So it quantifies the how much energy dissipates per cycle to the energy total vibration energy. So could we measure delta in real life structures like after an earthquake? Definitely. Sensors can record free vibration response after an event. So put the sensors, you can record the free vibration responses by identifying the peak amplitudes over time. So you identify the amplitudes, peak amplitudes, and you can calculate the delta and monitor the energy dissipation. Significant changes in delta could indicate that damage in stiffness, loss, or material fatigue. What are the typical values for structures? What are the typical delta values for structures? that's 0.02 to 0.04, and steel frames it's 0.01 to 0.03, wood structures is 0.04 to 0.08. Masonry or well damped one may have higher values. The mostly damped systems delta has less than 0.1. So if you know this, if you know the delta and energy, we can estimate the damping ratio. For light damping, the damping ratio is delta by 2 pi. This lets us categorize the damping from wire-based data without direct force measurements. So just by measuring the two successive amplitudes, we gain deep insights into the system's damping and energy loss. That's the power of vibration theory. So we can see the logarithmic decrement, that is the natural logarithm of x1 by x2. Energy loss is delta equal to 2 times delta into u. Physical meaning is half in delta equal to half by delta u by u. Damping ratio estimate delta by 2 pi. What happens if I pull this spring and let go? It moves back and forth, right? That's called vibration. The ball moves on up and down because of the spring pulls it back. Guys, what happens if I pull this spring and let go? It bounces back and forth, right? That's called vibration. The ball moves up and down because of the spring pulls it back, right? And the spring pulls it back, so the ball moves up and down. That's the reason it's vibrating, right? So that's called vibration. I learned that each time it bounces, it doesn't go as high as before. So each time when it vibrates, it doesn't go as high as before, right? That's because it loses some energy due to damping. Why does it lose energy? Is it the spring tired? No, not exactly. It's because something called damping. Like when you slide on the floor, when you are sliding on the floor, the friction slows you down. The spring and ball lose energy to the air and friction. The spring and the ball both lose energy to the air and friction. So if I measure how high the ball goes after the first bounce and then second bounce, can I find out how much energy is lost? So this is a question, like after I measure how high the ball goes in the first bounce, goes after the first bounce and after the second bounce, can I find out how much energy is lost? Yes. Let's call the first height as x1 and second height as x2. The difference tells us how much the vibration is slowing down. The difference tells us how much the vibration is slowing down amplitude, and there's a cool formula that called logarithmic decrement. Natural logarithm x1 by x2. This means we take the natural logarithm of the ratio of two heights. This is just the ratio of two heights and the natural logarithm. So this natural logarithm, that sounds tricky. Can you explain? Imagine the ball bounces really fast and height shrinks exponentially. This formula helps us turn that shrinking into an easy number to understand. Can we see how energy changes? Can we see how energy changes? The energy in the spring, the first ball is at the top, is like 1 by 2k x squared. That's the spring stiffness, x is height. At the first bounce, energy is this one. At the second bounce, energy is this one. We know the height decreases by e power minus delta. So energy decreases by e power minus delta square. So that means e power minus 2 delta. How much energy did the ball lose then? The energy lost each bounce is delta u is u1 minus u2. That's going to be 1 by 20kx and square 1 minus e power minus 2 delta. But that looks complicated. Can we make it simpler? Can you make it simpler? If the damping is small, the ball does not lose much height. If the damping is small, the ball does not lose much height. Then we can take this e power minus 2 delta is 1 minus 2 delta. So energy lost becomes delta equal to approximately 2 times delta into u1. So that means like half into delta u by u1. So logarithmic decrement is the half the fraction of energy lost per bounce. Tells how much energy the ball loses every time it bounces. And the smaller this delta, the longer the ball bounces before stopping. So this, can we use this to check if something's broken, like swing or polygon slide? If the delta changes, it means system might have damage or extra friction. So just by measuring two more sides, we can learn about the energy loss and system health. Hello everyone. Hey everyone. Look at the spring ball. If I pull the ball and let it go, it will bounce back and forth, right? The bounce is called vibration. The spring pulls the ball back and keeps moving it until it stops. Why does it stop? It doesn't bounce forever, right? The ball gets slower and slower each time it moves, because what's causing that? That's because something called damping. It's like when you slide on the floor, the friction slows you down. The air and the springs won't resistance take energy from the ball, so it loses the energy every bounce. So if you look at the height the ball reaches each time it bounces, we can see how much energy it loses, right? Exactly. Let's call the height at the first bounce x1, height at the next bounce x2. The height gets smaller each time because the ball loses energy. That's a special way to measure this loss called logarithmic increment. That's the formula. This means you take the natural logarithm of ratio of two successive heights. So what's natural logarithm? Is it hard? It sounds tricky, but think of it as a way to turn shrinking heights into a simpler number. The ball's height doesn't just go down a little bit; it shrinks exponentially. That means the height gets smaller and faster in a special way. Using logarithmic helps us understand that better. Why does the height shrink exponentially? Why not just go down by the same amount? The motion of the ball on the spring follows this rule. E power minus rho omega dt makes the height shrink exponentially because the ball damping removes the energy continuously as time goes on. Okay, what about the energy? How does height relate to energy? Energy stored in the spring when the ball is at highest point, like potential energy. The formula is this one, and how stiff, K is how stiff, X is the height of the displacement. So the first bounce the energy is this much. The second bounce we can see the height is smaller. Alright, so the energy at the second bounce is this much. E power minus because the height shrinks by e power minus delta, the energy shrinks by e power minus delta square. How much does the energy ball lose each time? That's the energy lost per bounce is delta u1 minus u2. This tells the difference in the energy between the two bounces. The formula looks complicated. Can we make it easier? Yes, we can. For small damping, delta is very small. We can use approximation. E power minus 2 delta is 1 minus 2 delta. The energy lost becomes this value. So wait. So delta equals half the energy lost divided by energy stored. This is the energy lost by energy stored, half of that. Is that right? Exactly. This means logarithmic decrement tells us the fraction of energy lost in every bounce compared to the total energy the ball at its highest point. So if delta is small, the ball bounces many times before stopping. If delta is big, it stops quickly. Yes, that's the idea. The bigger the damping, faster energy is lost, quicker the vibration stops. Can we use this idea in real life? Let me check if a swing or building is safe. Engineers will measure vibrations in building software at events like earthquakes by calculating the delta. They see how much energy is lost if the structure is damaged. What about the damping ratio? How is that related to delta? For light damping ratio is approximately delta by 2 pi. This lets engineers estimate the damping easily from vibration measurements. So by just measuring the two bounce heights, we learn a lot about energy, safety, and how things move. That's the power of physics. Simple measurements tell us deep secrets about the world. I want to try bouncing the ball and measuring the next. Let's do it. We will write down the heights and calculate delta together. Learning science is fun when we see how things really work.